the year. If you don't know me, I'm Dr. Hosnagel. I'm one of the math faculty in the department, and a person who has the honor of introducing our speakers every week. So we're pleased to bring back one of our alumna, Margo Morton. She graduated in 2015 as a computer science major, and now she's been at Nationwide as a software engineer for the last 4.5 years. Pretty much since she graduated, and while there she's been developing exciting prototypes for their innovation team. She is the champion of code quality, leading 2 enterprise-wide communities in test automation and cybersecurity, which if you're interested in our cybersecurity program, she hopefully will share some of that. While she's been at Nationwide, she decreased failures of their largest insurance quoting app by 60% and increased test coverage by 24%, which is awesome. And she's used big data tools to analyze patterns in test failure, decrease failure rate for one application from 75% down to 13%. So awesome. So she's going to talk to us about quantifying software quality and also share a little bit about her time here in post-Wittenberg. So let's give Margo a nice warm welcome.
But I'll start off by saying that it's great to be on this side of the lecture hall instead of taking my physics exam on the other side. I don't miss that. So let's talk about my journey and like where I was coming from. So in the beginning, before college, I had a lot of interest in computer science, and I had dabbled in computer science related topics. I was trying to build a website called Kitty Sprinkles that was about creating a cat character. And it was supposed to be a website, but I had no back-end development knowledge, so I had no way to bring this to life. And I thought, well, let me just major in this, and then I can do cool things like make the Kitty Sprinkles site. And during university, one of the great things that I got to do was attend these colloquia. So I'm going to recommend to everyone here, attend these, eat these snacks, come to these lectures. They will influence you in ways that you may not yet know. There were 2 really important things. The first that was really influential for me was this cybersecurity colloquium that I attended. There was somebody talking about air-gapped attacks that they were able to do against these systems, and I was just mind blown. I was like, wow, how do we secure these systems against such intricate attacks? And before then, I had never even considered cybersecurity as a profession. I thought, well, that's a little bit over my head. I don't know the first thing about that. There's some really advanced math. That's not for me. But after that, I thought to myself, maybe that is something, if I have this passion, this interest in it, that's something I could pursue. Remember, software wasn't something I pursued until university anyway, so really, if you have a passion for something, start pursuing it sooner rather than later. Then software quality. I think it was in one of Shelburne's lectures that we talked about the case study of the Therac 25, which was does anyone know this? Raise your hand if you've heard this story before. It's really, yeah, Shelburne knows it. This was a radiation machine, and it was created to deliver a dosage of radiation to a patient. However, this radiation machine, you would expect it to be, well tested. You would expect it to perform as intended 100% of the time. It mostly did that, but there was one major bug in it, and that was an integer overflow bug. And if you had hit this integer overflow, it would fail silently and deliver another extra dose of radiation. Some people, when they kept hitting this loop, not seeing the failure and continuing to run the program, these people would get over 100 times radiation exposure than they were supposed to get. Can you believe failing 100 times and not having any warning to the user? What a mess. Actual people's lives were hurt very badly with this. Now, thankfully, I write insurance software and nobody's life really depends on me, but I take all programs as if it were the Therac 25, thinking, what kinds of lives am I impacting and how could the failures hurt real people? Okay, so then in university, one thing that I really enjoyed was the chance to do a departmental honors program, and I worked on mouse analysis. The idea was that there are mice that need to be genetically analyzed to see what kind of species they are. And there's two very similar species of mice. You can see them right up there. The task was, can a computer sufficiently distinguish these two mice just from images alone? And this was really before Google's big image recognition algorithm came to the market. So now all of this is just throw this out. But there was some great math that went into this. We developed a binary logistic regression function, and we were able to get, with about 95% accuracy with the data set, correct morphological analysis of these mice. And we were able to present it at the ASB conference, and you can see my poster still out there if you want to learn more about mice. Ask me about mice sometime. I took a whole year on this project. After university, I was very thankful. I worked with somebody here who put me in contact with an alum who worked at Tech Systems, and we were in contact my whole senior year. I was talking about what kinds of jobs I want, what kinds of opportunities I'm interested in. I was like, I loved working on my biology project. I really want to work for a research lab doing computer biology stuff. And they were like, great, how about you start on this insurance company? And I was like, that's not at all what I wanted. But I was like, okay, sure, I'll work at Nationwide. And what are some preconceived notions you might have about insurance companies? Probably that they're boring, and that they do a lot of math. They also do a lot of computer science, as it turns out. There's all these big applications that businesses and people use to get insurance quotes, and there's all of these systems that communicate with each other. So if you are in a computer science path, it might be really interesting to look at big companies with large systems that you get to work on, because there's tons of really interesting jobs. There's over 200 teams who work on software at Nationwide, teams being as big as like 20, 30 people. So really a lot of great opportunities. That is the API team that I worked on for 2 years. The Restafarians, we worked on REST APIs together. Okay, and I have been really privileged to work on a lot of wonderful projects. I've been in mobile application development, website development, I've done back-end systems, front-end systems, and I've done test automation development. And in the beginning, I was thrown onto test automation development without having ever done any test automation development before. I was like, okay, I can write tests, I can write code, I can write code that tests other code. So we're going to talk about that now. So let's talk about, we'll start in the beginning, in the history of software quality. We should start with Grace Hopper. Grace Hopper was a Navy admiral and a computer scientist, and she wrote the very famous programming language COBOL. Here, as you can see, that's a moth. That was the first bug in any code ever found. She had this big machine that was probably as long as this whole table, and a moth got stuck in it and was jamming everything up, and she had to debug the machine by prying the bug out of the machine. And that was the first bug that was caught in code. Now, this is very cute, but when we're talking about bugs in applications, they're not these ephemeral things that exist outside of the machine. They're in the machine. They're in the code that's executing on the machine. So we're going to dive deep, understanding that bugs aren't this external concept. So let's think about bugs. Let's do a thought experiment. How many people think they've ever written bug-free code? Yeah. Well, the trouble is that at one point I thought that too. I was on a new greenfield project. Everything we're starting from scratch. We were following best practices. I was with some of the top minds of the company writing this program, and I thought there's no way that us, like 5 developers who are super great at our jobs could write a single bug in our program. As it turns out, I, halfway through writing it, decided maybe I should have something to verify my thought that we don't have any bugs in our program. So I run something that I'm going to talk about later called static code analysis, and we found 700 bugs in our program. Now, this program was a couple thousand lines long, and this is not an unusual amount of bugs, believe it or not. It's not that a program has like 1 or 2 major bugs. It's littered with them. In fact, when you look at the industry average, you've got 690 bugs per 1,000 lines of code. That's a huge amount. Now, the good news is that with some attention, with some proper care, you can debug your software by looking at it. Now, if you look here, you can see that, if you spend absolutely no time reviewing your code, you're going to end up with a huge bug rate in your code. And whereas down here, the best code is when you are reviewing a large amount of the code. So you would think that, given that this is well known across the industry, people would review their code, right? False. Nobody really reviews code by hand because the real trouble is just the magnitude of the problem you're trying to solve. Some software can go from a couple thousand lines to 50 million lines of some operating systems. Nobody's going to go 50 million lines of code by hand trying to parse each one, figure out what could possibly go wrong. Nobody's going to reasonably do that. The trouble is that people then take that to the other extreme. Like, if I'm not going to do it for 50 million lines of code, I'm not going to do it for 100 lines of code. And in fact, many organizations, 22% don't do a single code review manually at all. So, hope you don't trust your software too much. So we know the problem and we know the solution. We're just bad at applying the solution, and that's because manually it's very difficult to do and very time consuming. In the beginning, there were manual testers. Manual testers would compare the program behavior to the requirements by literally sitting down at the computer. They would type things out, they would try and break it to find the bugs. Now this is very time consuming and labor intensive and hard to repeat. Let's say you want to show somebody a bug, then you have to sit down and you have to get them to come over and then you have to do the whole process again. And if somebody else wants to do it, you have to write it down and send it to them. And a human exercising a program takes a large amount of time. So then automated testing came about, and it's a robot pretending it's a human executing the code. So this runs much faster. Robots can do things much faster than humans can. So let's say you have an automated test to check the text of a web page. It can do that in a couple milliseconds, whereas a human might do that in a couple minutes, for example. You have an increase in quality in bugs per 1,000 lines of code. So when I started out, I was in test automation development, and I was tasked with writing acceptance tests. Really, my job description was make sure that our largest applications have quality. And my team said, the way you make large applications have quality is you write acceptance tests for them. And I was, being new to everything, I was like, okay, let's do that. Let's write acceptance tests. And I was thinking, well, how do you know when everything's been tested? An acceptance test is when you have your code, you write code that exercises other code to test and see if it behaves correctly. So you give it inputs and you expect certain outputs, and then you just do those checks over and over. But how do you know when you tested everything? You don't have the original code in front of you, so there's really no way to know. And in fact, does writing more tests mean more quality? Is there diminishing returns? I didn't really see the relationship between acceptance testing and code quality. And the reason why I didn't see it is because it's really there nebulously at best. Acceptance testing is in fact not the one true way to find quality of your application, as I was originally led to believe. It's black box testing. So it's like if you were given a running car and you have to find every bug in it by pushing the buttons and driving this car. Okay, you could probably find some bugs in that. But the better way to do it would be to look at the car's source code that executes all the commands that the car follows, or to open the hood and peek in to see that the engine isn't connected correctly, or that this one rope looks like it's dangerously close to falling off the belt. And then, acceptance tests being black box tests, they're prone to what I have coined non-deterministic test hell. Non-deterministic test hell, it's when you have regressions that appear when you run something multiple times and nothing has changed. Look at that. That's, 6 passing tests in your run number 1. And here we've got 5 passing tests and 1 failing test, and nothing about the application under test has changed except some time passed between those 2 runs. What does that mean? it could mean anything. It could mean that, maybe a server went down, maybe your data is bad. But the problem with non-deterministic test hell, or even worse when there's more than one failure and they change places over time, this means people are going to stop trusting the results. When I talked earlier, when Professor Hufnagel introduced me and talked about how reducing failures in the applications was one of the things that I worked on, that's a huge deal. Being able to take your test results and parse through them and figure out which ones are actual failures, which ones are false failures, which ones are non-deterministic test hell failures, and being able to reduce those and get a set of tests that accurately test the system. That's what we're aiming for. We need a standard measuring stick of software quality that's not prone to this garbage. So my theory is that there's really only two components of software that can be analyzed, and that is the code itself, so the program that you write, and then the environment it is running in. So it as a runtime program can be evaluated as well. Now the acceptance testing, this is exercised against a running program, like a running car. But the code itself is something that we didn't originally look at when I started out. So we're going to look at these two facets of code quality. And I've made this beautiful chart. Look how gorgeous these colors are. Trying to lay out all the aspects of code quality. I'm trying to make this such that each of these sets are as full and non-intersecting as possible. So this is the least and most amount of testing you should have to do. The exact right amount of testing you should do. So we've got things that you can do against the code itself on this side, and then the running program on this side, and we've got some cross-cutting things as well. So you might have heard from the cybersecurity courses about cybersecurity, and you might think, oh, well, the way you test an application for cybersecurity is being a hacker and you run a bunch of commands against it. Well, there's also ways to look at the source code itself and figure out what the security vulnerabilities might be just from that. So I've been trying to think in my head, if I were to make a function to represent software quality, I'm still chugging on this one, so bear with me. But the trouble is that I'm trying to take a vector and put it into a percentage, and that just, it's not fitting together very right. So we're going to just do an example so that you can sort of see the value that this might have compared to just knowing the total number of failures altogether. Let's say, remember my original example where I wrote that program and I had run the static code analysis and I had 764 failures. Is that good? Is that bad? How bad is 764 failures? Can you quantify that? I don't know, it's a number. Is that worse than 10 million failures? And if so, how much worse? So I really wanted to project this onto a percentage because people have this notion of percentages. Obviously 12% is much worse than 80% by a significant degree. So let's say you start off with 100, and then 2 of your tests are failing. So we've got 2 out of 10 tests, for example. And then let's say we've got 680 issues that our code analysis finds. And we've got, let's say, 1,000 lines of code. If we go through this, that would be 100 minus 20 minus 68. That would be a 12% goodness of your software. So you can sort of see how you can quantify it a little bit. Something with more tests would have, or more tests passing would have higher quality, and so you can sort of start to evaluate from there. The trouble is that these are weighted equally, which is what I'm still trying to work through. So we're going to go through each one of those different types of software quality aspects. And I'm not going to dive real deep, but I just want to spark your interest in them. Think of the ways that you can test software, things that you may not have even heard of or thought about, as I hadn't when I had started out. Maintainability. So there's a team I worked on, and they were very timid with code. They had a program, and they just put their full trust in that program. It ran, but nobody could touch it. If you touched it, it would be cursed or haunted or something, or it might fail, so nobody can touch it. But the trouble is that, fearing to touch code in case that it might break, that's not a good plan. You know, eventually something is going to break down, whether it's inside of your code or outside of your code, something you can't even control. Eventually you're going to have to get down in there. And one piece of advice that I want to give to everyone is from this really excellent book, The Pragmatic Programmer. If you have any interest in computer science, pick up this book or ask for it for Christmas. It's an expensive book. One really great example from this book is that you must fix broken windows. In New York, they found that when the windows of a building are broken, more windows get broken and graffiti starts to appear on the building and people will break into it. And so they were thinking, well, this is a huge problem. You know, this is bad for our city. We don't want people to keep destroying our buildings. It's already got a broken window. Well, the broken window is a problem in your code that everyone just like tiptoes around. Like, oh, we can't touch it. We might break everything. Well, if your code is trash, then people will trash your code as well, just like with the buildings in New York. If you have a broken window, if people see that you don't have any comments anywhere, well, they'll also just not write comments anywhere. If they see your code is literally spaghetti, they'll write spaghetti code too. So we're going to start off with one way to maintain your software, and that is calculating the cyclomatic complexity. And that's a large phrase for something that's very simple, and that is figuring out how many paths, branching paths, there are in your algorithms. The theory is that if there's more than 10, your program is not good. Branching paths being a while loop, an if statement, a for loop. Each one of these things adds complexity, and you can think of them as nodes on a graph, like if this, then this, you know, else this. So this would be 2 branches, 2 nodes, right? So if you have a bunch of if statements in a function, you're doing something wrong. Having a tool count these up for you and tell you what methods are the most bad is very convenient and helps you prioritize what kinds of things you look at as you're fixing your code. Another thing, which is a method that we should be careful with, but is still important as it tells us some good information, and that is the lines of code, or the LOC. Lines of code gives you a general estimate of like what your code is that you're dealing with. Operating system, 50 million lines of code. Or open source library that is a calculator, I don't know, maybe 2,000 lines of code. So there's a huge gambit, and we can't compare small programs to the 50 million lines of code programs very easily unless we take into account lines of code in our comparisons. So some different ways that we can calculate this is logical lines of code or physical lines of code, and that's just whether you minimize everything and just count the lines themselves, or if you count the entire thing, including your paragraph long comments. Another thing we can do is analysis, and I foreshadowed static code analysis before. Static code analysis is basically like your friend going through your code and telling you everything that looks wrong to them as they read it. It's basically your best friend. Static code analysis looks at all sorts of great ways your code could be bad and uses formal methods to prove how bad your code is. It's great. It's fantastic. I recommend that everybody just look up static code analysis, how it works behind the scenes, and if there's static code analysis for one of the languages that you work in. Code coverage. Code coverage is a really important metric when testing is involved. We're going to get at testing the next section, but code coverage is how many times each line of the program has executed. You want 100% of the lines of your program to execute, but if you've got a high cyclomatic complexity, you are going to have very few lines of your code covered, most likely by your standard tests, because you probably don't have conditions that go through every single branch. You probably just have a couple conditions that test the main things and then call it a day. So what this does is it gives you a counter. You see that right there? It goes and it shows that these never executed at all, and that's a bad deal. It hides it in red. No good. So in this example, we've got an if statement, but only the first part of the statement has been tested. So they've written one test, which is good and commendable, but their test didn't take into account all the options. And we're going to talk about how to write good tests pretty soon. We're going to use this beautiful mathematical concept called equivalence classes. hope that that's covered here somewhere. Okay, so testing. We're going to jump back to the acceptance testing that I did before. Really, we were going about it the wrong way. Or we were going about it in one way, but we didn't get the full picture because we didn't have the full breadth of the application covered. We were just exercising it from the outside. Now, I'm going to suggest the right way to test a program is through these three methods. You've got unit testing, integration testing, and user interface testing. Unit testing tests that it behaves according to the requirements. API testing checks that information is passed between systems correctly. And UI testing verifies that a user can navigate the whole application flow. So, if we take a look at each one of these, we can see that a unit test, from its name, just tests a unit. No kidding, Margo. You use the source code to write your unit tests. The unit tests literally test the code itself. So you need to have your unit tests in your source code for them to work. You can't write unit tests as an external application testing your source code. That just won't work. Now your integration tests and UI tests will utilize a separate code base or a separate framework, potentially. And they will look at the larger picture when different classes talk to each other, different parts of the program send information across to each other. And what I really want you to take a look at here is the speed. Now, what you can glean here is that from top to bottom, we have increasing slowness. And this is important in a big enterprise when we have huge applications, thousands of lines, hundreds of thousands of lines. You know what would be the worst? If we did everything by hand. But thankfully we don't do everything by hand. The second worst would be if we just did all of the UI testing and had that be the majority of our testing, because those tests are very slow. We had one application that was so slow to test, you would start it at the beginning of the month. It would end at the end of the month. You'd release your code, and then you'd start running it again, hoping that it would be ready for the next code release the next month. Now, thankfully, we're far beyond that. But you can see that if your tests are slow, you're not going to be able to react very quickly or agilely to them. So imagine you have a big code base, and you have a release at the end of the month. And your testing team, having run their tests that month, found 5 major defects in your code. What do? Well, you have to go develop again and fix them and then test them again, so we'll just throw it into the next month's release, right? This is bad. Really, this is a trouble with a test strategy. What you want to do is you want to prioritize the fast-running, quick, instant feedback tests, and then have fewer and fewer long-running tests at the end of things. So let's deep dive into unit testing. Unit testing, I gave this hand-waving example that tests units, but you can think of a unit as a method or a job that the program performs. It's the smallest testable part of any piece of software, which is obviously a method. The trouble is that as you wait longer and longer from having written the code, defects and bugs become more costly to fix. What happens, so you'll commit your code, there's a bug in it, and then the bug is found, somebody tells you about it, you have to go back, you have to program it to be good, you throw it back to the other person, they're like, okay, I'm testing it, it's good now, and you're like, okay, great. And now imagine that times 10, and that is enterprise software development. Equivalence classes are a very neat way to describe all the ways that valid inputs and outputs of a function should behave in relationship to each other. And your test cases should reflect this. So let's say you see this age field. Let's pretend this is part of a form of a website. Now, if this was a naive tester, what they might do is they might just have a test that runs every single possible number in the whole world to this and be like, okay, we've tested everything. That's great. Very good. Nice job. The trouble is that it's costly to test every single possible input to a function. And so you really just want to get it down to what is the bare bones tests that we can write that covers every single case and have some randomization in there just for fun. So an equivalence class defines this as, okay, well, this is a field that accepts any value from 18 to 60. So it should return some sort of invalid result if it's less than 18, valid if it's 18 to 60, and invalid if it's greater than 61. So you'll have 3 different test cases, perhaps picking a number from those ranges each time that's different, so that you have a nice gambit. But you wouldn't have 100 tests, for example. Some unit testing libraries, obviously this will depend on what your source code is, because it has to read your source code and execute against it. Integration testing, this is testing that the components talk to each other correctly. So one example, there was another radiation delivery machine, and it had a very bad flaw. The bad flaw was that nobody had really done integration testing very thoroughly. It would calculate the dosage, it would save it to the database, it would be read from the database, and it would, apply that dosage. Nobody tested the database reading and writing very well because it was off by like a factor of 10. Nobody really checked that the decimal place was in the right spot, and that it was getting written correctly and read correctly. And so the trouble is there, like maybe the code performed exactly as it should have. It calculated the dosage, it applied the dosage, and the database behaved exactly as it should have. It would have passed all its tests, it writes data correctly, it reads data correctly. But when they talked to each other, there was something wrong with that. Something was not validated in that space. So that's why integration testing is important. Even if you have unit tests for your whole code, your code interacts with other things, most likely like a database or another piece of code, and you want to make sure that that interaction is correct. UI testing. UI testing is an interesting subject. Basically, it's exercising the code as an end user would. So maybe you're not going into the methods of the code. You would be launching the website and getting an insurance quote and checking that your policy papers were generated correctly. Another aspect of UI testing is accessibility testing. This is something that the US legislation has passed in a recent year. Basically, they want all websites to be accessible by people with disabilities. So like your color scheme has to be just right for eyesight, and it has to be screen reader accessible. This is the sort of thing that UI testing would fall under. Now, you're like, okay, well UI testing is really just testing the underlying code, so why do we even really have to do that? I'll give an example of why you really have to do that. I was working on the nationwide mobile application, and there was an input field on the mobile app where you could input the amount that you wanted to pay for a certain bill. And it worked fine in our unit tests, and it worked fine in our integration tests. It wasn't until we had a physical phone in front of us that we were typing the numbers in, we saw that because of some weird JavaScript bug, it moved the cursor back to the left every time. So you would expect, the cursor to move right as you typed. Well, you would type a number, and then you would get right back to the beginning, and then you type another number, but it was in the front and not the end. And so, you want to pay $6.50, you would end up paying $56. So this is very bad for the end user. So obviously, things like that are caught on the UI testing phase, and it's very important not to skip. Now this is the most time-consuming and expensive kind of testing, so you want to make sure that you cover all your cases, but only those cases. You don't want the majority of your testing to be UI testing. Okay, now the really fun part is security. Security is a big topic, and I'm really glad that Wittenberg is covering cybersecurity, because this is a field that really deserves a lot more attention than it does. And here's some reasons why. Here we have a hacker. And this hacker is responsible for some of the nearly 200,000 total cyber incidents in America last year, with 7 billion records exposed. Probably one of your records is in them. $5 billion financial impact. And here's the kicker. 93% of the breaches could have been prevented if you had applied these techniques. Now, the trouble is that these techniques are not necessarily taught, and they're not often shared. So here I am, sharing and teaching. We're going to talk about something that's pretty interesting called static code analysis for security, which is static application security testing. Basically what this does, this is like if your friend was a cybersecurity expert and he's like looking over your code and being like, that's a vulnerable library you're using there, take that out. This is white box testing. And what that means is that it's the opposite of black box testing. You're like, Margo, what the heck are you talking about? White box testing is basically where you see what you're testing. Black box is where it's hidden from you. So in the beginning, I was doing black box testing of the application when I was throwing test cases against it to see what would stick. White box testing is if I was looking at the application itself. So what this does is this looks at the source code for known vulnerabilities, and then it gives you remediation suggestions. So here it said that they're allowing an untrusted piece of information to go into the program without sanitizing it first. There's some really good SAST libraries. Find sec bugs is a good one for a couple common languages like Java. DAST is its counterpart. So if you remember back to the big diagram where you had the two sides of the testing, you had the source code analysis side and you had the running application side. Well, this is on the running application side. This is if your best friend, the hacker, was attacking your application that you wrote. Basically, this is a program that acts as a user who is trying to hack your code, trying to throw everything that it knows against it to get through and find some vulnerability. Now, you don't run this on software that's in production in your company. This is how you get fired. But you can run this on your own code, and this can make your code much more secure. It can protect you from a lot of well-known, highly utilized attacks. Somebody who should have used this technique is an organization we all hold in the highest regard, the IRS. They wrote an API, which is basically a system to expose data. They wrote this great system to let you be able to read your tax records through this API. And this was great. Okay, so you can log on, get your tax records flawless. The trouble, though, is that they didn't run DAST against it. Otherwise, they would have found that they did not secure it properly, and you could brute force other people's logins very simply. And if you were one of 100,000 lucky users, your tax records were published for everyone to check out. So all that, sensitive information like your marital status, your social security number, how much you make in a year, all that good stuff is out in the open. So that's why this sort of thing is important. Even though the program they were writing, a program to give people access to their tax records wasn't like a radiation machine, it still had serious consequences to the end user for not having followed these steps. Harm came to people because their records were exposed. Okay, now there's one step further than DAST, and that is IAST. IAST is interactive application security testing. And this is really cool because what it does is like a combination of SAST and DAST. It smashes them together. You have this program and you put it inside of your program and it sits there and it watches everything that happens from inside of your code. So let's say your code is a website and you write some user information to a database and maybe display something else on the page. It would look at everything that happens from the user typing in their information to that entering your function, to that function calling the database connection, to that data getting saved in the database. It will follow the whole string of events. It has access to HTTP requests, your libraries, your data, your methods, and it follows every single flow of information to find where it started and where it ended up, and what kinds of ways it could be manipulated between there to end up in a vulnerability. So IAST, incredibly effective, highly recommended tool. This can give you insights for ways that people could access your code in ways that SAST and DAST just couldn't do. Okay, so another thing that's really important to talk about is software composition analysis, sometimes also called dependency scanning. Basically, this gives you insight into the libraries that you use in your program. So whenever you have like an import statement at the top, there's code that somebody else has written that you want to use because it's useful to you and it's ridiculous to write everything from scratch all the time. You include it. Now, you can write the best, most bug-free software that's ever been written, but this library that you're importing, who the heck knows what the quality is of that? Maybe it has a huge security vulnerability. Who here has heard of Equifax? Yeah, okay, so the trouble with Equifax was that they did not do software composition analysis. The Equifax data breach was one of those 93% entirely preventable attacks. They had, so, I had my records stolen in that attack. It can happen to real people. What happened was that they didn't use this tool. And what happened was that they had a vulnerable library in their code. The vulnerability was published 2 months. They had 2 months of notice to change their version to the secure version that did not have this vulnerability. And they just sat on their hands. They didn't do anything about it. They didn't update their version. They just let it happen. They were like, we'll take a gamble. Who will really exploit this attack? And they gambled on people's records, my records, your records. This was preventable. 143 million people's records were exposed in this really sensitive personal data. So, it's recommended that you always check the vulnerabilities in the dependencies that you have and update them as needed. There was another one. This one was really interesting. I write a library that handles REST requests, API, remember the Restafarians? So I wrote a program for that the enterprise uses, and many students use it as well. And it has this one library called REST client, and that is the dependency that I use to facilitate those REST requests. It's really convenient. It's a simple, elegant, fast library. It was a perfect tool for the job. But the problem was that a couple weeks ago, this library, some hacker stole the person, his login information, the person who published this library. They stole his info. They hacked his account. They used his account to publish a vulnerable version of this software that didn't exist before. They published it as an older version, so maybe people wouldn't notice right away, and it took people weeks to notice. What happened was that every single time an HTTP call was made, they would route this, I think it was to the Ukraine, and it would participate in a Bitcoin mining operation. So now your computer was part of this big, like a Bitcoin honeypot. It was just awful. So make sure that you're always on the lookout. Vulnerabilities are found all the time. And the reason that all these security tools exist is that you don't have to be the expert. You don't have to know a single dang thing about security to run these tools. And in fact, it's troubling if people think that they are the expert in security because these things happen all the time. You should never think that you're the expert in your field because somebody's going to prove you wrong. In this case, you should use known sources like the National Vulnerability Database to check your dependencies often. My closing thoughts are that all software has bugs. If you think you've written bug-free software, it hasn't happened. It's never happened. The most tested software in the whole world is NASA's Space Shuttle Control software. This has existed from the beginning, and hundreds of people touch it, and they have a 35 million year quality budget. No company has that much money to throw at quality. So if anybody could have the most perfect software, it would be NASA. And you know what? They have got it down to one bug in 4,200,000 lines of code. So not so bad, but it just goes to show you that we're all aiming to be as good as possible, but perfection is not reachable. That doesn't mean that the goal is worthless. It doesn't mean that achieving perfection is worthless to strive for. It just means that you got to be, reasonable. When your code comes back with 764 failures, that's not a failure on you personally. It's just an example of how much you can be better. And what I found is that I've actually grown the most in my career when I take this feedback from these tools and be like, okay, I really could have written that better. Okay, maybe this part of the program is kind of bad. Maybe there's better ways of doing things. Maybe there's better libraries to use. And I've learned so much. I feel like this has almost been like a mentor to me to use these tools. So I think that if any of these tools were interesting to you, check them out later, make a note, ask me about them. And I think that developing software is as much of an art as it is a science. There's this metaphor going around lately in the field that software writing is like craftsmanship of an art, where like you start out as an apprentice and then you go to journeyman and then you become an expert and you can train other people, and it's really sort of like that. You've got to have that eye for quality, you've got to have that desire to be good at your craft, and you know, knowing that there's not just one right way of doing things, but there are best practices and better ways of doing things. It's important to keep in mind. So I wish that, you know, starting off I had all this information available to me, but now, you know, lucky for you, you have all of this presented in a nice, easy format. Another thing that I really want to do is give some advice. One thing that was really instrumental to me in setting up my career was coming to these colloquia and getting involved in the thesis and really figuring out my passions early on and then pursuing those things in my career. Because once you find something that you have an interest in, have a passion about, that means that you're not going to really find it difficult to work on. You're going to be enthusiastic, you're going to be eager. You know, not everyone's going to get up here and be excited to talk about cyclomatic complexity for 50 minutes, but I am. You know, somebody has to care, and that person is me. So find what lights you up and really pursue that. That's something that I couldn't overstate. Make sure to invest that time in yourself and come to the colloquia, eat the pizza, get some knowledge. Thank you.